What's so great about geometry by construction? Well, we get to make the stuff we're talking about very quickly. We work in Euclidean space and hyperbolic space at the same time. Euclidean space is all this stuff, everything in this plane. But hyperbolic space is only inside this outer circle, this bigger circle. Usually radius 1, Euclidean radius 1. So that's the stuff, that's it. So we have a hyperbolic circle. That's this guy centered at O, radius OB. That's a hyperbolic circle. And I'd like to construct a circle of the same size, but in a different location. In fact, I want to make a circle the same size as this, but passing through O. So that's what we're going to do. So we start out with making the inverse of point B. This is a Euclidean construction because it's leaving the space, so we must be doing a Euclidean construction. You know, we're going outside of hyperbolic space. And we're using Euclidean rules. You can see these nice straight things. Now, we do have a hyperbolic ray, but this guy here is not a hyperbolic object because in hyperbolic geometry, there's only certain kinds of things that can be hyperbolic lines, and that's not one of them. The only straight things that can be hyperbolic lines have to go through O. We'll see some more stuff. Now, that's B and B inverse right here. Next step in the construction is make a segment, a Euclidean segment from B to B inverse, get its midpoint, which I called C, and then construct this, this radical axis, this segment that joins the 2 points of intersection of the two circles. So we're going to use this stuff to make the next thing, which is a circle. This circle centered at E, that's the Euclidean center. It actually has hyperbolic center B. We're done. This circle is actually congruent to the circle centered at O going through B, this other green circle. Those two circles are the same size in hyperbolic measure, and we can actually prove it. We don't need that stuff anymore. Let's see why this green circle, this one here that I'm pointing to, is the same size as that green circle. So here's the actual reason why. Oh, but before we go there, this red arc in here is a hyperbolic line. It goes through a point and its inverse across the big circle. That's one of the ways you can tell you have a hyperbolic line. Another way is these two, this red circle and this green circle, meet at a right angle if you measure with tangents. Now, here's how we know that these two circles meet at a right angle, besides that they just look like it. Here's the proof. If I were to invert the point D across circle C, I would go the perpendicular from D up to the circle at the point P, do CP, and then do a right angle over to there. Now, that's how we found this point. We know that this circle is perpendicular to the big circle there. So the radius from OP has to be perpendicular to the radius from PC. So I already know I have this right angle. Well, that means that the inverse of point D across circle C is the point O. Now let's look at circle E, the circle centered at E, this guy right here. It passes through O and D. O and D are inverse points across circle O. So that means that this green circle must be perpendicular to the red circle. Well, if that's the case, then this hyperbolic line is perpendicular to this hyperbolic circle, which means it contains a diameter. So here's a diameter of the green circle, a hyperbolic diameter, and here's a diameter of that smaller green circle. They meet at B. B has to be the hyperbolic center of the hyperbolic circle, whose Euclidean center is E, but B is the hyperbolic center, which means that OB, radius of the larger green circle, is congruent to BD, radius of the smaller green circle. But they're the same size in hyperbolic distance because this is the hyperbolic center of this circle. So this circle has to be the same size as that circle. They'd have the same area. That's the kind of stuff we do in this geometry. In this book, we make the things we talk about and we prove why it is so.